review. Remember what we said? We said that if we wanted to, the calculus solved an important problem. It allowed us to take some random function, and instead of just being able to calculate an average rate of change, which was the slope of a secant line, and what was the definition of a secant line again?
F of x plus delta x.
Okay, sure. That's the slope. Okay, but what is a secant line? Secant line. Not the slope of a secant line. Just in general, what is a secant line? Okay, it crosses the function in two places and maybe more. You know, we don't care about the other ones, but it crosses in two places, so we can calculate an average rate of change by using the slope of that line, right?
Yeah.
So in this case, if it crossed here at x and at x plus delta x, by drawing that secant line and drawing a slope triangle and coming up with the slope of the secant line, we're able to calculate an average rate of change, right? Okay, but the problem was, how do we calculate an instantaneous rate of change? Now, we came up with a good solution to this. Now, and let's put this in another context that might be a good way of kind of conceptualizing this. If we want to calculate how fast we're going, let's say as we cross by, you know, that big grain elevator on the way to Hermiston on the side of the road there. Everybody knows the grain elevator. So, what's it called? That one. That one.
Really quick, are we recording?
I'm recording, thank you. I am recording. So if it takes me, how far is Hermiston? 35 miles? Say, something like that. 17? No, it's more than that. Okay, I'm just going to say for the sake of argument, to make the numbers easy, let's say it's 30 miles. Okay, so and let's say it takes us 30 minutes to get there. What's my average speed?
60
miles an hour. Okay. So does that mean that I'm going exactly 60 when I go by that elevator? No, maybe, but not necessarily, right? If I wanted to get a more accurate estimate of how fast I'm going when I go by that grain elevator, maybe I ought to instead maybe take like a mile interval around that grain elevator, right? And if I go that mile in exactly 1 minute, how fast am I going? 60. So that would be maybe a tighter estimate then, right? Because now, but even then, is that perfect?
Nope.
Okay. What can I do to make the estimate even better?
Just check your thing when you drive by.
Okay, but my speedometer's broken though. That's the part I forgot to tell you. Raise your hand, please.
You know you're using cruise control though.
Oh, okay. No, my cruise is busted too.
Wow, you should just get
You
I should. I need a new car. Okay. What can I do?
Wait, what are we trying to do?
I'm trying to get a more accurate estimate of how fast I'm going when I pass by that grain elevator.
We're gonna take a tan thing.
Okay, true. Yeah, we're getting to that. But if I didn't have access to the mathematical tools as I'm driving my car, couldn't I even maybe just take like a shorter distance even? What if I just went 100 meters and timed that? Or if I went 10 meters and timed that? And if I really want to get accurate, I could actually maybe just go for like a second or something,
Wouldn't it be
right?
a little
10
difficult
meters
though,
would be
because
less than a second.
meters just in miles per hour?
Well, okay, yeah, it's true. I mean, the calculation might be more difficult, but if I did the calculation, it would be a better estimate, right? The point being, the shorter the interval, the more accurate the estimate is going to be of my instantaneous speed, right? Make sense?
Yeah.
Okay, and so we took that to the extreme with calculus. What calculus lets us do is say, well, let's not even constrain ourselves to some finite distance. Let's instead let the length of the interval over which I'm timing this shrink to 0, right? So graphically, what we set up here on just generically on just a random function, not a physics issue at all, but just f of x, if we want to know what the slope of the curve is, aka the slope of the tangent line, at x, all we have to do is take the slope of the secant line and take the limit as what goes to 0? Delta x goes to 0, right? So we're gonna, and what that does visually is it takes this other point that forms the secant line and it draws it back towards x until we let that distance go to 0 and the 2 points merge to 1 point. And so the secant line becomes a tangent line, right? Because the tangent is the is the line that grazes the function at one point only, right? Okay, that is pretty slick. That's what calculus does for us. So we went through the whole exercise then of saying, okay, if that's true, then this is our general form for what we're now going to call the derivative of a function, right? This tells us for any function, we just leave it f for now, but for any function that we choose, if we apply this, this is going to give us back the derivative function, okay? We looked at first an example where we said, okay, let's take the function f of x equals x squared, and let's find the slope of the tangent line at x equals 3. And we got an answer, right? We got an answer when we went through this of 6, but then we said, okay, well, we could even do better than that. Why limit ourselves to saying only at x equals 3? Why don't we just find what the slope of the tangent line is going to be for any value of x? Let's leave x as a variable and therefore completely general, and let's come up with an answer. And when we did that, we did some review, and we got this, didn't we?
Yeah,
We said,
yes, we did.
when all the dust settled, we came up with the derivative function, started with f of x equals x squared. We came up with f prime of x, the derivative, as being 2x, which was really powerful, because what that said is now we don't have to specify the value of x. We can do that later. This is going to work for all values. For this particular function, if I want to know the slope of the curve at x equals 13.3, what is it? 26.6, because all I have to do is just plug in that x value, and this function is going to give me back the slope of the function, right?
Right.
Slick, okay? Let's look at these two things together. Let's look at the, yes. Let's look at the graphs of these two functions, and I want you to notice something really important about this.
What two functions?
The function and its derivative, okay, on the same graph. You're getting a lot of mileage out of what we're about to do, because this is exactly the stuff we're going to start talking about in physics today. So.
Can we just go to the lab?
No.
Oh, motion. We didn't do that. We didn't. Like you could have done it. No, it did not work. So there was like a crash on that one. You could like, they gave you a graph and you could like build a frame. That's like a graph with speed on it. And they did want to line it on.
I don't think we'll find it either.
What? Oh, play one? Yeah, they take it out. Yeah, I heard that.
Why?
That was on CNN. It was on CNN.
What's he doing?
Motion. If you talk about motion and not working, it's like, I think it's like some type of other code changes to make it PG-13. What?
Well, that's what they're known for. They should change things.
Well, no, it's so, because apparently, like, so now people just start like reading the articles in it and stuff. 'Cause apparently there's actually good articles on it. Never. So.
Why is it doing that? Why can't I just get that one?
The editor said the 12-year-old in me is very disappointed in the like current version of me.
I bet you guys are happy
Gosh.
Why did they change it?
So little kids can have it?
Ah,
So we could have it at the.
I give up. Anyway, oh, there it is.
So you start it now.
Okay, look, please. Look, please. Okay. Okay. So the blue function is what?
The derivative.
Okay, that's the function, right? That's the x squared, right? So. Probably can't draw on that, can I? No, okay. Anyway, blue function is x squared. The red function is the derivative, right? Now, here's what I want you to see. The axes are a little bit messed up here. Just so we can see the parabola better, I compressed the vertical axis. So, you know, going up 1, 2, 3, 4, 5, that's 5 on the vertical axis, and that's only 1 on the horizontal axis. We can untweak that in a second, but for now, this will be good. So describe, now our ants all of a sudden, they have evolved further. Not only do our calculus ants know their x and y coordinates on the graph now, they're developing the ability to sense the slope of the curve that they are walking on. How about that? These are highly evolved super ants. Super ants. So if an ant is walking along the blue function, and let's say he's right there at the origin, what is the slope of the function? In other words, the slope of the tangent line to the curve there?
X squared.
0, right? Everybody agree? Because if I drew that line in, it would just be the tangent would be horizontal there, wouldn't it? Right?
Yes,
Whereas if I went up here somewhere, the tangent line is going to be steeper and positive, right? Over here, the ant is going to sense what kind of a slope? Negative and bigger, right? Okay. So do you see here that the values of the derivative function directly correspond to what the ant's slope sensor is telling him or her, right? When the ant, notice right here that the value of the red derivative function is what? 0. Up here, the value of the red derivative function is positive and big, right? Down here, the value is positive and smaller. Over here, the value is negative and relatively small, because it's not very steep. But back up here, it's negative and large, steeper, right? You see that?
Yeah.
I want you, that's really important to be able to do, to be able to see that there's a connection there, right? The red and the blue are related by that slope of the blue function is the value of the red function, right?
Not just because it hits the 2 points.
No, it's only hitting 1 point, right? I mean, these two graphs, I superimpose them on the same graph, but what they really are, remember, is this is the blue one, the original function, and the red one is the derivative of the original function, right? So this is the one that gives us back slope, and this is the one that just gives us back value of the function, right? Does that make sense? Let me just make this point. If I calculate, why is it doing that? I think something's not working. This is not good. Oh, it's just a big, maybe that's a little much. I got you, it is working. It'd be kind of fun, but I'm not. So, f of 2 is what? Actually, 2 is a bad one. Let me do f of 3. What's f of 3?
9.
9. What's f prime? We should make that red.
Oh, 6. Oh.
Yeah, good. F prime of 3 is 6, right?
Yeah.
Okay, if I go to my, if I go here, well, if I go over to 3, the value of the function is 9, right? If I go over to 3, the value of the derivative function is 6. See what I'm saying? Right? So the point is, the derivative of the blue function, meaning the slope of the blue function for any value of x, is represented by the values of the red function.
So when the blue was 9 and the red was 6, that is.
Well, just because we happen to pick an x value. If we evaluate the blue function at 3, it gives us back 9, because f of 3, 3 squared is 9. The value of the derivative function at x equals 3 is 6. And so what that's telling us is the slope, right? The slope of the blue function right there, the slope is positive 6. Because it's skewed, it doesn't look like positive 6, but we can see that in the value of the red function. Yes, Jennifer?
So the derivative line is always the f prime?
Yes, the derivative, our notation for that is f prime. There'll be some other notations we'll use also, but for now, that's a good one. Yep.
So each function only has one derivative?
Yes, yeah, it does, because if it's a function, it can only have one slope. Well, hold that thought, because we're gonna run into one of the things we're gonna discuss here today is where do derivatives exist and where do they not exist? And what we're gonna see is that derivatives, and it'll make sense, but derivatives might not exist in places where functions exist. And you'll see why. It'll be perfectly clear when we talk about it, but for now, just dig that. Okay, so let's practice this once though. Let's do an example. Here's our function. F of x equals, how about if we do x cubed minus 2x. I want to calculate the derivative function from that. Now, let's start together, and then I'm going to turn you loose to work on this a little bit. So where do we always, for now, where do we always start when we want to calculate a derivative? Hunter, where do we start? Maybe somebody better help him out, because he wasn't paying great attention. Where do we start with? Okay, so we got to start with our, okay, the limit of the slope of a secant line, right? So we know that in general, f prime of x is always going to equal the limit of, what was that slope of a secant line?
2f of x plus delta x minus f of x divided by delta x.
Good. And don't think about that in terms of a formula because you'll forget it. Think about it in terms of a rise over a run, right? You always want to think about it in terms of this picture.
Is there a song for this one?
There isn't a, we can make one up, but there isn't one. Yeah, maybe that'll be one of our songs. We're gonna make up a song. Right, here's the picture, right?
Yes.
If this is x and this is x plus delta x, then the difference in the y values, remember that's just gonna be f of x plus delta x minus f of x, there's the rise, and the run is just delta x. So that's what that means, right? That when we talk about the slope of a secant line, that's what it means. This is called, actually, something that we will refer to in the future. This whole thing right here, this whole animal is called the difference quotient. Difference. Okay, so the slope of a secant line we define as the difference quotient. I don't care if you know that. I mean, it's not a big deal, but that's what people might call it. So we start general. Now what do we do?
Go big.
We go specific, don't we? Right? So this is what our f of x actually is. And so we're going to take this general template and we're going to apply it to our specific function, right? So try that. Everybody do this. You can come up with, just go through step one. I just want to know when I do this, what is f of x is going to equal the limit of what specifically? Okay, go.
I don't know.
Okay, real quick, I'll give you just kind of a hint. F of x is defined as x cubed minus 2x. What's f of a?
Oh, a cubed minus 2x.
Good. What's f of hand?
Hand.
Hand cubed minus 2 hand, right? Okay, what's f of cow? Cow cubed minus 2 cow. I mean, you get the idea. There's a pattern, right?
No.
The input, I'm just doing this stuff to whatever the input is, complicated or simple. What is f of the quantity a plus b?
A plus b
A plus b cubed minus 2 times
a plus b.
a plus b. Good, right? So you got the idea. So you can do this. Set it up.
Set it up.
You're gonna give us some time, right?
I'll give you a couple minutes.
I can put this in.
Yeah.
Wait, do you want us to?
I want you to fill in, I want you to write what I'm going to write there before I write it. Oh. Yeah.
I don't think I'm good at
Sure.
this.
Give it, what's that?
Oh, yeah, right.
No, I thought.
Wait, I don't get it.
Okay.
Because you put it in.
Why am I not seeing Sarah?
She's at doctor's appointment.
Oh, that's why, okay.
She should be back at business.
Okay,
Oh, she's not busy.
well, yep. Wait. Okay, now we'll almost. Yeah, well, see, now, every place I have an X, I'm gonna have to input the quantity X plus delta X, right? For f of X plus delta X, okay? Good, okay, now that's gotta be in parentheses.
Victoria, what's the formula for Q?
For Q, I don't care if you go that far,
Okay, good.
you have to go that far.
Victoria,
That's what I want.
is this right? So far, I'm
Okay, that's good, but something's wrong with that. Think what this needs to be. Every place I had an X in f of X, I have to substitute the quantity X plus delta X. Okay. Okay, let's have a little look. I know not everyone's probably done, but you're far enough, I bet. Okay, I'd like to know here, let's see. Hunter, what's the first part? What's f of X plus delta X gonna be?
X cubed minus 2x delta
X, okay, X cubed minus, say it again?
2x.
2X delta X?
Yeah.
Okay, does anybody disagree? Okay, we got some disagreement, so let's go back a little bit. Okay, good, good. Every place, now think about the pattern. Here's the pattern, right? X is our input, but really what this is saying is f of input equals input cubed minus 2 times input, right?
Yeah.
What's the input though? The input this time is that whole quantity x plus delta x, right? So I've got to have, instead of an x cubed, I'm going to get,
plus delta X cubed.
good, x plus delta x cubed minus 2 times,
X,
okay, so that part right there,
Okay.
that part is f of x plus delta x, right?
Yes.
Okay, good. Minus f of x. Agreed?
Yeah.
Okay? All over as, good, okay? So now we got a little algebra to do. I'm going to resist the temptation to go through Pascal's triangle right now, but I will. By the end of the week, we'll go through it. Yes?
Just a quick question, why is it that for the first part of the quotient you used the f of x, but then the second part you just kept going with the limit? You know what I mean?
Well, no, it's the limit of the whole thing. Right? It's the limit of all this big quotient.
Yeah, but why is it that for the first part you used the x cubed minus 2x function, but then on the minus you used the f of x?
Well, I did, right? Because f of x is, one more time, f of hand is hand cubed minus 2 hand, right?
Yeah.
Well, for the first part here, what's hand? Well, it's x plus delta x. So it's hand cubed minus 2 hand, right? That's this part. Let me color code it. So this part right here corresponds to that part right there,
Yeah,
right?
but why is it reflected in the same pattern that the f of x is?
Okay, because look at this pattern. F of x, we're subtracting f of x, and that's f of x. See? Okay?
So you're subbing in x plus delta x for
Right.
the x in the first function.
Okay? Agreed? Okay? I'll let you stare at that for a second. Okay, give me a 1 to, flash me a covert 1 to 5 here. 5 meaning 100%, got it, 100%. 1 meaning not at all, or somewhere. Okay, well, okay, we're looking pretty good. That's good. All right. So we see how we got to here, right?
Yeah.
Okay, now if I were to try to evaluate this limit directly, we're just going to get x, that's going to become x, that's going to become x. I'm going to get x cubed minus 2x minus the quantity x cubed minus 0 over 0, right?
Yeah.
Okay, so we have to do, and we kind of predicted that, right? The difference quotient will always be indeterminate until you do something with it, until you do some algebra. So the algebra here is probably going to be what? Expanding and canceling, and we can kind of predict even based on yesterday probably what's going to happen. All of the naked terms are going to cancel, right? So we're going to be able to factor out a delta x in the top that will cancel with the bottom, which is going to leave us with our derivative function. So it's always kind of the same game we're playing. It's just different functions every time, right? So let's do this then. Let's go through the math. So on the top, can anybody tell me what x plus delta x quantity cubed is? X cubed plus 3 x squared delta x plus 3x squared plus delta x cubed minus, if I distribute the 2, minus 2x minus 2 delta x, right? So that's, there's that part, right?
Okay, so please tell me that's all the time.
No, it's just that one quotient.
Right?
Okay, I think I got it now.
Oh, okay.
Okay, I'll pause. Everybody see that?
Should we put
Well, I distributed, so I don't have to.
Let's expand the other one.
Okay?
Whoa. What
Right.
about the negative 2x plus square root x? Oh, you did that? Oh, secretly? Yeah.
I'm sorry.
Secretly. I tried to hide it from you, but I did put it up there.
Where did we get the 3x squared delta x?
Okay?
From the cube thing.
From this. This part right here becomes,
Isn't that parentheses? The best part supposed to be parentheses?
okay, but I got rid of the parentheses by distributing. Remember,
A
I'm trying to,
negative? You distributed a negative?
Yep.
Oh, I see,
distribute
I
it,
see.
right? See it? Because that's what I want to do, right? I want to expand this whole thing out so I can combine like terms and cancel
Yes.
terms that, right? Okay, everybody with me?
Yeah.
Okay? So we get some good cancellation here. Look, the x cubed cancels with the x
The
cubed.
negative 2x and positive.
Good, the negative 2x and the positive 2x cancel, right?
That's pretty much it.
Okay, that's it.
Okay.
But that's good, because that leaves us with, look what happens, that leaves us with the limit of, you tell me all the other terms. So I've got on the top, I've got 3x squared delta x,
3x delta x squared and then plus delta x.
yep, minus,
Minus 2 delta x. Over delta x.
okay, what can I do on the top?
Take out a delta x.
Good. What am I left with?
3x squared.
3x plus delta x squared minus 2.
Okay,
Yeah, plus those things.
ah, those cancel to 1, right? That's a delta x.
And then pulling out the 0.
You're just putting.
Okay, good, so we canceled it. Now, because we canceled it, the indeterminacy has been removed. We canceled the offending factors, right? The factors that made it indeterminate are gone, so now we can directly evaluate. When we directly evaluate, all the terms that have a factor of delta x are going to do what? Go to 0. So that guy goes to 0, that guy goes to 0, and we're left with,
But all the delta x's go to 0?
yes, right? Because that's our limit. We're now we're taking the limit, right?
Plugging it in.
Plugging it in, right? We're directly evaluating, okay?
Wow.
And so that's our derivative. So we get f prime of x equals
What if,
3x squared minus 2.
so now what do we do with that thing?
That's what we wanted. That's what tells us the slope of the function at any value of x we choose. So if I want to know, Cheyenne, you tell me please, what is the slope of this function when x equals 2?
Okay, so that would be 1 second. 34.
Good.
What?
F prime of 2 would be 3 times 2 squared is, maybe not quite that high. Try it again.
Oh, God. Oh, but not. Because it's
10.
Wait,
Okay.
how?
Okay, here's how, watch please. Shh. Because if I just evaluate this function at x equals 2, I get 3 times 2 squared is 12, minus 2 is 10.
I was doing 3 times 2 squared.
There you go. Okay, gotcha. Gotcha. Okay, so that's amazing. Now we know the value of this function, the value of the slope of the curve any place we want because we have derived the derivative function, right? We've come up with, the verb we use in calculus is we differentiate, but we'll get there. We took the derivative and we found it, okay? Do you have a question, Sam?
Yeah, what was the original function?
So the original function was
So we just kind of simplified it, right?
was that. Okay.
Wait, if we, what's the point of knowing the can if we already
Okay,
know the
please raise your hand and talk. Yes, Delaney's got the floor. Go ahead.
What if we already know the curve?
Well, this
Why do we
is a
even
little
know the tan
this is a little different though, right?
of the,
This is going to be a slightly different function. It is going to be a parabola, but it's going to be a different one. And so what this tells us, I mean, yeah, sure, we could, I guess, if we had graphic technology at our fingertips, we could graph this thing and ask a really smart graphing utility to tell us what the slope of the curve is at any given point. But we don't always want to do that. I mean, we want to be able to just analytically say, can we come up with a new function that's different than this one that represents the slope of the curve of this function, which we just did. Yeah.
So f of x prime only finds the slope. not
F prime of x is the slope, exactly. Yep, the slope, exactly.
the slope of the derivative?
Of the original function.
Okay.
So once we find the slope, then what?
Well, right now that may not seem like a big deal, but very soon, well, fairly soon, that's going to be one of the most important things we talk about is slope, because where this gets applied is, for example, if we want to determine, let's say, here's a hypothetical situation that you'll be able to solve very soon. Let's say that we are going to build soup cans for our calculus brand stew that we're going to sell as a fundraiser so we can go on a field trip. Okay, so anyway, when we're doing this, we want to do two things. We find out that it costs us to do, the cans come in pieces that have to get assembled. And the barrel, the lateral part of the can, the tube part of the can, it costs us, it turns out that it costs us 1.2 cents per square inch of surface area. The lids are a little cheaper. The lids are only 0.9 cents per square inch. And we're going to enclose exactly 12 ounces of calculus brand stew in each can. We want to know, how are we going to configure the cans? What are going to be the dimensions of the cylinder that are going to make our costs a minimum so we can have our profits be a maximum? Okay, that has to do with a derivative function that we're going to develop, a cost function, and we're going to want to know the slope of that curve eventually, because what we want to do is we want to find, when we graph this thing, it's a good question, I want to make sure I answer this. If this is cost, and let's say this is going to be this is going to be the radius of the can, let's say. Okay, so we're going to get something like this maybe. We're going to get some function that maybe goes like that. And right there is the point that we want, where the slope is equal to what? 0. Yeah, that 0 slope is going to correspond to a minimum value of cost, right? So knowing the slope is huge. We got to know what the slope function is, what the derivative is, so we can find the zeros of that. And we're looking ahead quite a bit. If this seems a little cryptic and confusing, I wouldn't be surprised, but we'll kind of work our way towards this. But I just want you to have a glimpse ahead why we're doing this, right? So we want to be able to come up with a derivative function so we can solve analytical problems like this. This is what we might call an optimization problem in calculus. It's a heavy hitter in calculus. It's one of the big deals that in the first half of the year that we learn how to do. Really, the purpose is largely to do stuff like this. Okay? So we got to be able to come up with this function. It's very important to us that we can come up with that. All right? Okay? All right, so now that we get the idea, and we did one. That was a hard one. Let's look at let's look at something else. I want you to tell me, okay, how about this? For the blue function, it's going to be a regular parabola. Okay, that's f of x equals x squared, right? Ant walking along that is going to always be able to sense a slope, isn't he?
Yeah.
Okay. What about this one? What if I do, let's say, an absolute value function? Well, that was bad. So this one is f of x equals the absolute value of x. Okay, just visually, this is an easy one to work with because the lines are all straight. You tell me, what is the ant's slope sensor going to read right there?
2, 2.
What's the slope going to be?
1.
1, right? So in other words, f, let's call this one g instead of f, so we can keep the two separate. So g of x is the absolute value of x. G of 2 equals 1, right? Or g prime of 2, sorry, right? Does that make sense? That says derivative, right? The derivative of this function evaluated at 2, we don't even have to take the derivative. We can just see visually that the slope is 1, right? Because that all that means is the slope, right? Okay, what is
So
g? Go ahead.
Won't you still sense the slope because it's getting like uphill?
He will. It's 1, right? He rises 1 and runs 1. He senses a slope of 1 there, right? Okay, what is g prime of negative 2? Negative 1, right? Right here, wouldn't you agree that the slope equals negative 1, the slope of the tangent line? The tangent line is exactly on the curve there, right?
Yeah.
Yes.
So you have to have the graph to figure that out.
No, we wouldn't have to. We could do this as a piecewise function. But I just want to look at, right now, I don't really care about the analytical method. I just want you to just be able to relate to, just for a second, just being able to look at this and say, well, now I don't even need to do calculus. I can just see the slope, right? Okay, but here's the problem. What is he going to sense right there?
0, 0.
Ah, okay, we got a problem. We got a problem. Because the ant, the slope is necessarily related to the adjacent points, isn't it? Think about this. If the ant is on the curve right here, the tangent line has that slope because the points next to the point of tangency create that tangent line. Does that make sense? In other words, as I zoom in closer and closer and closer on the function and the curvature disappears, remember the analogy about space. If we're standing in a wheat field, the earth looks pretty flat, but from the moon we can block it out with our thumb because the curvature is, we're so far away that we can see the curvature better, right? As we zoom in on something, like if I took a little patch of this curve right here and I just zoomed in and zoomed in and zoomed in, it would start to look straight, wouldn't it?
Yeah.
Everybody, I mean, I'm not going to do it. You can all relate to that, right?
Yeah.
Yeah.
So as I get closer and closer and closer, this curve, the blue curve and the purple tangent line would look identical as I zoomed in eventually, right?
Yeah.
Okay? What about right here, though? As I zoom in on this point, does the curve ever flatten out?
No.
It never does. It's always pointing. It always looks like that, right? It always looks like a 90-degree angle.
Okay.
See what I'm saying?
Yeah.
And so that's a different kind of a thing. The tangent line can never truly match up with the curve no matter how much I focus in on it, right? Because if the ant takes a small step to the right, and it could be arbitrarily small, meaning as small as you want, he's always going to experience a slope of positive 1. If he takes an arbitrarily small step to the left, he always experiences a slope of negative 1.
So
Up
that
here,
means
that's
it's
not the case. Say it again.
So that means it's not possible.
That's right. So we can't define a slope there. Up here, going to the right or the left, he would always experience the same slope if he takes a small step, right?
So would that make it more difficult closer to 0?
So what it means is that the derivative, listen please, the derivative function cannot be defined at a sharp corner in a function. Because at a sharp corner, there's no such thing as a slope, right? Okay, so that's one of the several places we're gonna discuss where derivatives don't exist. It's a sharp corner. That's an important one. We call that a
What about for the x squared, the parabola?
the parabola would be fine, because it's not sharp, it's blunt, right? It's a smooth end on it. So if I looked at a parabola and I focus in, it's gonna look flat
So
as I get real close.
the has to be a pretty small.
It literally has to be a sharp corner where it's, no matter how much I focus in, it always looks sharp. Okay? All right.
What about